Welcome to LFI Educates. Today we are going to continue with this chapter number 4. Today our topic will be, the first topic will be Ampere's Circuital Law. It states that the line integral of the magnetic field around any closed path in vacuum is equal to mu naught times the current enclosed by the curve. I'll write down here. It states that the line integral of the magnetic field we write it as B around any closed path in vacuum is equal to mu naught times the current enclosed by the curve, mu naught times the net current enclosed by the curve or the closed path. Here the line integral of the magnetic field, so surely line must be there. dl is our line integral of the magnetic field. So vector quantity, the length there also we take it as vector b dot dl around a closed curve is equal to mu naught times the net current enclosed by the curve. It goes like this. Suppose if I take one wire, you all know that the field line will be circular at a certain point. If I choose a point on the wire when current I is passing, that point will give a circular loop, or we say that magnetic field is developed. So if you take any point, near to the wire, because of this point where the current is flowing, because of that you will draw the magnetic field line, and that magnetic field line will be called as the Amperian loop. At this point, if I want to find out the magnetic field, then I'll say here B dot dl. dl, this small portion of the magnetic field, I'll take it as dl here. Then I'll integrate it. If I integrate, the line integral means that integration of this line, the closed loop, the Amperian loop. If I integrate it, then that will be equal to mu naught times, mu naught is the magnetic permeability, and the net current. The net current means, while drawing this field line is produced because of the current passing through a particular point in the wire, only one point. So the amount of current flowing through it here will be, I net will be simply I. But if I take the length of the wire a little bit long, because of this, then here it will appear as like a ring. For all the points, one circle will be formed. For all the points, one circle will be formed. So the Amperian loop will look like a ring type of structure. If I further extend the amount of current in the wire, the ring will become fatter and fatter. or this way if I draw, for one point I'll get one ring. If I take another point, then I'll get another ring. If I take one more point, I'll get another ring. If I take all the points, then the whole ring will appear together, will appear to be like this. A big ring will be formed, like your finger ring, you can say. So the amount of current flowing through this length of the wire, if I pass current I, it will not remain I. How many points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 suppose. 13 times I it will be. That's what it says, the net current. Because of that current, what field is formed? That current we call it as net current. And multiply with magnetic permeability. This is your Ampere circuital law. Let us apply this. Let us see its applications one by one. The first application of Ampere circuital law is to find the magnetic field due to a long straight conductor carrying current. And in this case, we'll take a long wire. Let us take the hardboard as I have shown you before. This is your infinitely long straight wire XY. Here you are allowing current I to pass through the wire. You will make one small hole here in the cardboard and then allow to pass the wire. In this case, I want to suppose find out the magnetic field at a certain point. Suppose here I am choosing that point as P due to this point in the wire at a distance R. Then what I'll have to do is I'll draw the Amperian loop now. At this point, if I draw the magnetic field line, that will form the Amperian loop, like this will form. Now, when the current is passing from bottom to top, as you know, the field direction, it will be anti-clockwise. It's coming from bottom to top. With your thumb rule, you can find out it will be anti-clockwise. It is curling like this, anti-clockwise. Now, if it is anti-clockwise, I will mark it this way, the direction of the field line, and that itself will be your Amperian loop. Now, direction of magnetic field dB or B will be tangential. As it is in a circular path, it will be tangential. At the same time, the point which you have chosen is DL. DL you have to choose along the Amperian loop. This is your DL. Now DL also will be pointing. If I draw a circle, if I take a small portion, then it will be a tangent. The direction will be tangent to the circle. So DL also will be pointing in the same direction. DL is also pointing in the same direction. The angle between B and DL, it will be 0 degree. On the board it looks like as if it is going up, but it is, the circle is like this, and at this point if I take P, then it is going tangentially. DL is also going tangentially, B is also going tangentially. So let me write down here like this. Let XY be a long wire. You don't know the exact length of the wire. Let P be any point near the wire. where the magnetic field is to be determined. Now we draw an Amperean loop passing through P. So first we'll draw the Amperean loop passing through P. That P be any point near the wire at a distance r from the wire. At a distance r from the wire where the magnetic field is to be determined. After that, we will draw the Amperean loop passing through the point P. Then we will use Ampere's circuital law at point P using Ampere's circuital law at P. The line integral of the magnetic field around a closed path is equal to mu naught times the net current threading the circuit or enclosed by the curve. So B dot dl, if you operate dot product, then you get like this: B dl cos theta is equal to, here mu naught times the net current. This field line is formed because of one single point. So at a single point the current flowing is I only. So you write simply I, the net current will be I here. If the loop is formed because of some region of the wire, then you have to take the whole length of the wire. Then in that case, as I said, it will form a ring. It will not be a single line. In this case, the angle between B and DL, as you can see, is 0 degree. So B DL cos 0 degree is equal to mu naught times the current I. Then integration B is a constant term, you can take it out. Magnetic field. Integration is a line integral. As we say, line integral will integrate only the line. Cos 0 degree is equal to 1. So don't need to write anything. So mu naught I. Since cos 0 degree is equal to 1. So B, then DL. If you integrate DL, you took a small region of the loop. This is DL. If you take the whole thing, it is the circumference of the circle. So it will be 2 pi r. 2 pi r is equal to mu naught I. So you need your magnetic field B. So your ultimate formula will be mu naught divided by 2 pi I divided by R. This is the expression for magnetic field for a long straight conductor of infinite length, that is XY. We don't know the length. We don't know the exact length. So this is the expression for magnetic field. This is your first application. Let us see the second application. Magnetic field solenoid. A solenoid is an insulated long wire in the form of a helix. Like this will look. Insulated wire having a large number of turns. But the solenoid is a very long one. When we draw, it appears as if it is very short, but you should know that a solenoid is actually like this. Diameter or the radius is very, very small compared with its length. The length of the solenoid is large as compared to its radius. Radius is very, very small. This way you have to take. You have to think. Suppose this is your solenoid, and then you are allowing current I to pass through the solenoid. The current is in this direction. All throughout if you draw. So the current is passing in this way and is leaving out from this end. Now to find out the magnetic field inside the solenoid, we consider the Amperian loop in this form. In the form of a rectangle we take, and we'll name it as A, B, C and D here, and the length of the solenoid we'll take it as L, or the length of this rectangular loop, or we call it as Amperian loop, we'll take it as L. And we know that the magnetic field line inside the solenoid will be in one direction. Suppose if I take A, B, C, D, there will be some confusion because B is used for magnetic field. So I'll take this as P, Q, this one I'll take it as R, and this one I'll take it as S. So that the direction of magnetic field line, here I am marking it. It is in one direction from left to right. There is B. This is your magnetic field inside the solenoid. And this is the length of the wire. PQ is the length of the solenoid as well as the length of the Amperian loop. We'll take like this. Consider a rectangular Amperian loop, or simply loop PQRS, where PQ is equal to L, the length of the solenoid, or simply you can take PQ is equal to L. Now to apply Ampere's circuital law, the line integral of the magnetic field is B dot dl across the whole loop PQRS is equal to mu naught times the net current enclosed by the loop or the curve. Then here this PQRS will divide it into four different parts: PQ, QR, PS, RS. Will divide it. This way you can divide it. B dot dl along PQ, then plus QR B dot dl plus RS B dot dl then SP B dot dl. Here this, they are not forming loop, so if you don't put the circle also okay, it's not forming a closed path. It is a straight line. PQ is a straight line, QR is a straight line, so you can take simply the integration. And here mu naught times, what is the net current, that you'll have to write down now. Here the net current, we write like this: number of turns per unit length is equal to number of turns divided by the length. So number of turns n, I want to introduce it, then it will be n into L. N times L, and the amount of current flowing is I. That means the current all along the length, or the number of turns. How many turns are there? That many currents you are following. Per turn, one turn, how much current is flowing? Then I. Then how many turns are there? Then NL. From here you will get it, NL. That gives us N number of turns. That will give us the total current here, or the net current. Then this one you can break up: PQ, BDL, dot product operated cos. For PQ, DL, the length of the wire, L we are writing here, DL is in this direction, B is also in this direction, so cos will be 0 degree. 0 degree plus QR, BDL, B and DL. B is in this direction. We are taking in QL. The length is, DL is this way. So here it's making an angle of 90 degree, like this. This is the length of the length of your loop. DL is along this direction, B is in this direction. So it will be 90 degree, cos 90 degree, plus along RS, B dot DL will be BDL cos. Here this value outside the loop, as I said earlier, when you are taking the solenoid, long solenoid with smaller radius, and the length of the solenoid is very long, then this goes away from the solenoid. The field strength is always less outside the solenoid. Generally this term we take it as 0. RS we take it as 0 plus along SP B dot DL, this is SP, DL is in this direction, B is in this direction, they are making an angle here also 90 degree. These two sides will become 90 degree. The angle between B and DL cos 90 degree, that is equal to mu naught and Li. Now as you know that cos 90 degree is equal to 0, this is also 0, this is already 0 by now, then this term only will remain. Only the first term will remain. There is integration of along PQ, BDL, cos 0 degree is equal to 1. So everything became 0. This is mu naught and Li. So B is a constant term, you can take it out. Integration of DL is equal to mu naught and Li. Then you have B, integration of DL. Integration of DL, that is from P to Q. That is length L, you can see here. The whole length you will take it as L, mu naught and Li. So L you can cancel it out. So ultimately B you will get mu naught and I. So this is the magnetic field of a long straight solenoid carrying current. But if this solenoid you are not keeping in vacuum, if you are keeping in a particular medium, suppose in air you are keeping, then this formula will slightly change. This is in vacuum. Magnetic field of a long solenoid in a medium it will appear like this. B is equal to mu of that particular medium, absolute permeability will come, mu and I, or you can write it as B is equal to mu naught, mu r, mu r is relative permeability, and times I. This is in a particular medium, or this one you can write it as like this also, because mu is equal to mu r into mu naught. This is the relation between relative permeability in vacuum and permeability of the medium, magnetic permeability of the medium. The third application of Ampere's circuital law magnetic field due to a toroid. When we say toroid, it is an endless solenoid made in the form of a ring. That structure we call it as toroid. Sometimes you may be thinking that why we are doing only for this solenoid and toroid. Actually, this solenoid and toroid are the equipments that we use generally for producing magnetic fields practically. Suppose let me draw one toroid here. Like this will look. Let the current passing through the toroid be I. I am allowing current I to pass through it. Now in this case, is it looking like a ring or not? It must look like a ring. Or you can even do, first you can draw one circle like this. After that you can wind up the coil. Now in this case, suppose as it is a ring, there will be a center here. Suppose say O. Like in solenoid, we have come across the magnetic field inside the solenoid is present, not sideways, not up, outside it is zero. Then here also, as it is a solenoid, a long solenoid having a turn, the magnetic field will be present inside the solenoid. But when we say inside here, it will form a ring. But when we say inside here, now where inside means, if it is like this, inside I can say here also it is inside, here also it is inside, here also it is inside. So everywhere it is present. So in this case, when we take the distance of the Amperian loop from the center of the toroid, this R we take it as the mean distance. Suppose if these 3 are there, the mean value, the 3 values we add it and divide by 3. Sum of observation divided by number of observation. It is not only that what you can see here, one circle, red circle, that is the Amperian loop. It can be nearby here also, it can be here also, it can be here also. Many you can draw. but R is, we are taking it as the mean radius of the Amperean loop. So now to find out the magnetic field inside the toroid, write down here that current I pass through the or flow through the toroid the Amperean loop is a circle of radius of mean radius R. Better we write mean radius R. So to apply Ampere's circuital law here, let us take this point as P. We are going to find out the magnetic field at a distance R from the center. There is the dl, suppose here itself is the dl. Let P be the point where the magnetic field is to be determined. And it is to be determined. Then use your Ampere's circuital law using Ampere's circuital law. The line integral of the magnetic field, you write down B dot dl is equal to mu naught times the net current. Now here B dot dl, we will find here B dot dl, it will be B dl cos. Here also the direction of magnetic field and there will be in the same direction, there will be tangential to it. B direction, dl direction, both are in the same order, so it is 0 degree. So we cos 0 degree equal to this integration and mu naught here net current, then the number of turns, how many number of turns are there, that will take it, and current is I, like the earlier case in solenoid, N I, where N is the number of turns. Then this is B, you can take out of integration, dl, you can integrate it, cos 0 degree is 1, mu naught, introduce this number of turns per unit length. As I said, number of turns per unit length is equal to n divided by L. So this n, if I want to replace, then number of turns per unit length into L will come, number of turns per unit length. Length, this one if you say length, this is circumference of the circle. Where L indicates circumference of the circle 2 pi r. So capital N will be n times 2 pi r, 2 pi r into I, the current that you are allowing to flow through the toroid. B here dl, the same thing, integration of dl. dl integration if you do, you will get 2 pi r. This is dl. The whole length of dl will be, the sum of it, the integration of it will be 2 pi r equal to mu naught n 2 pi r into I. These two terms, bracket terms, you can cancel it out. Then you will get the expression for magnetic field in a toroid, mu naught n I. Mu naught n I. This is the same expression that you got in solenoid. That means a solenoid and a toroid. the magnetic field inside the solenoid or the toroid, both are the same. And likewise, if the toroid is kept in a medium of permeability mu, then mu naught will be replaced with mu, and that mu can be replaced with mu naught into mu r, the relative permeability as well. So this is the expression. Let us do one numerical based on this. A toroid has a core of inner radius 25 cm and outer radius 26 cm. So here two radius are there. So what you have to do first is solution. Whenever you do toroid, mean radius you have to find, mean radius. That r we have written earlier in the derivation is the mean radius. R is equal to, so r1 plus r2 divided by 2. Mean find out, 25 plus 26, both are in centimeter, divided by 2. It is 51. 51 divided by 2. Centimeter will change it into meter, divided by 100. Then it will become meter here. 51 by 2 is 25.5. 10 to the power minus 2 meter. Like this, we'll find out the mean radius first. Then, around which number of turns is given? Number of turns. We use capital N for number of turns. It is 3500. And the current passing through the wire is 11 ampere. Current I is equal to 11 ampere. But we know that when you find out the magnetic field inside the solenoid or inside the toroid, outside the toroid we know that it is 0. The first answer is 0 directly, because there is no field outside the toroid. But for the second one, we are doing actually all this calculation inside the core of toroid. Then your formula is mu naught Ni. Small n. Small n is number of turns per unit length. So this you have to find out. That's why they have given you the number of turns. Now number of turns per unit length. If you write the small n, we know that number of turns per unit length is n is equal to n divided by L. N divided by L. And here this length L, the Amperian loop is a circle. So the length L we take it as 2 pi r, the circumference of the circle. So n will be number of turns divided by 2 pi r. Number of turns, that is n, divided by 2 pi r. Here n is 3500 divided by 2 pi, and radius, the mean radius, that is 25.5. 25.5 into 10 to the power minus 2. And this value we'll use to find out the magnetic field inside the toroid. The first case, if you do number 1, magnetic field outside the toroid is 0. As there is no magnetic field outside the toroid. Then the second one will do magnetic field inside the core of the toroid. Is equal to mu naught Ni. Now mu naught value, as you know, it is 4 pi into 10 to the power minus 7, and the number of turns per unit length, you can see here 3500 divided by 2 pi into 25.5 into 10 to the power minus 2, and the current here is 11 ampere. So like this you can write down the values, then you can calculate and get the result. Pi you can cancel, 2 times is 4, then see 2 into 11 is 22, then again you have into 3500, then 10 powers, or this value, one more 0 you can write and remove the decimal, 255, then 10 power you have minus 7, minus 2 will become plus 2 if it goes up, like this you can write down. Then these zeros, how many are there? 1, 2, 3, 4, 5, then it will become 10 power minus 2, 10 power minus 2, 35 into 22, this one you can cancel it, 5 7 to 35, 5 5 to 25, 5 1 are 5, these two can multiply, 22 into 7, 154, then divide by 51, 3 times, it is 153, 10 then decimal. After 50, you cannot divide, so 0 if you put here, 10 will come, 1 time will come, so you can write this nearly 3 into 10 to the power minus 2, or 0 1 also if you wish to write, you can write down Tesla, the SI unit of magnetic field. This way you can solve it. Thank you and have a nice day. Stay tuned with LFI Educates for the next upcoming video.